Good afternoon. Is this slide visible?
Yes, sir.
Okay. So, uh, what we were discussing in last class, that is called cards of dimensionality. So, what we have just who are new today and just the continuation of lecture, just recap what the problem. We are first understanding that what is the k nearest neighbor problem, and what we see that in k nearest neighbor, the main assumption of k nearest neighbor is that similar points share similar levels. That means that the points are drawn from a probability distribution are it in a Kenen setting that similar points is clustered together. So the distance between them means the similar points, or you can say the points belong to the same class, is in general less. So that was the assumption. But what we ultimately, in high dimensional space, these points that are drawn from a probability distribution tend to never be very close. Actually, this is a bit complicated thing, or better to say complicated to highlight, to visualize that what actually happened in higher dimensional space. And in mathematically, it can be shown that in high dimensional space, the points are very much further or very much distance to each other. In a, they're in a the distance between 2 points is very large in a high dimensional space. And that we try to understand here in a bit mathematical way. So to understand this is a very important concept actually, because lot of anomalies, what we will see in a later part of this machine learning, or in a next semester when you go to the deep learning, then this going to this, take a very crucial role to understand a very complicated concept. Okay. So what is the basic idea? What we have shown here that this is a cube, this is three-dimensional space, and this is a unit cube that one every the sides of these cubes that is a unit uh, measure. So if with L be the edge between the now within this cube, this is a smaller cube, and this smaller cube is what? It is basically a, let's say, k neighboring space, k nearest neighbor space, okay, within this cube, where the each edge is L. So if we say that the data points here are uniformly random, that is important. Uniformly random. Uniformly random means these are very uniformly distributed, but random distribution. Okay. Then we can say that in this space, the approximate number of points is how many? It is very close to k if it is a k neighbors nearest neighbor. Total number k, and if n, where n is the total number of points. Total number of points. From this by D. Okay. Okay. So now what we did, we calculate these values of different dimension, because now here L is equal 0.6, 0.63, 100, 0.95, and so on. It is a very, very high. So what does this mean? If we approximate this Q, this means, I think better to show in a different color. This is very, very high. Almost 9.99% is there. So if it is so much big space, now what happened? It has happened that there is a point here, star. This is the within this is nearest neighbor, and this is another point, this is dot. It is not nearest neighbor. But actually, from this point, if it is a cluster center, these 2 point is a much. These 2 point is not in a big distance. But still it is the nearest, it is within this, it is come the nearest neighbor, but this point is not. So the basic proposition of nearest neighbor has been failed here. If the dimensionality is high, the dimension is high. And this is called the cards of dimensionality. Okay, so that means if it is a higher dimensional space, that it will not work. Okay. Now, another way to understand, we can understand it. So here you can say, let this is understandable from, it is a single dimensional space. Single dimensional space. Now you see that we take a dimension, this is 0, just for example, and this is 1. Okay, this is the space. Okay. Now, what I'm trying to say, if I say what is the probability that that the point are not in the edge. Now, how edge is defined? Let edge is defined in this way. These are the edge points. So in between these points are the edge. So edge, let's say it's epsilon. So the total, if we say that this space in a single dimensional, it is 1 by 2 epsilon kind of thing. So probability is what? So probability is basically 1 by probability 1 minus 2 epsilon. Okay, so this is the probability. Or better to say this P is equal to probability of that what is the probability? Probability that the point are in the edge. Now it is in one dimension or one dimensional space. Now let's say we have to take a d-dimensional space. Now what is this probability? This is one dimensional probability, this is a d-dimensional probability. That is 1 minus 2 epsilon to the power d. Now what does this mean? 1 minus something, so it is less than 1, this quantity. And if it is less than 1 and to the power d is a very high number, then it is very much close to 0. So now what is the probability that the points are not in the edge? So not in the edge means in between. So then probability become very, very less. Actually, so what conclusion we can say? In higher dimensional space, points are, now points means they're uniformly distributed, are in general wide apart. The corresponding distance is very high. So if this is the case, then there is no neighborhood. If it is every point at in a very much distance, there is no neighborhood. And KNN fails. You understand? Now, can you say, is there any on the KNN? I'm definitely say on KNN or not other. For case of KNN, is there any countermeasure? Anybody?
Could you repeat the question again?
So you understand that what I'm trying to say here? Here I'm trying to say, if a higher dimensional space, KNN-like algorithm fails because there the neighborhood, what we have defined in case of KNN, it doesn't happen. So it doesn't exist. The neighborhood itself, every point are very further apart to every other point. So there is no neighborhood as such. What we have defined in case of lower dimensional case, 2D, 3D in for KNN. Understand this? Now, my question is now this is the first thing you understand. And then the question is there any countermeasure?
Hello, sir.
Can I?
Sir, could we project the higher dimensional space to a lower dimensional space?
No, that is different. That is differently.
Can we change our definition of the neighborhood rather than Euclidean distance? Perhaps that can help.
No, even that distance I'm saying now, that distance, that is definitely not a Euclidean distance. What I'm trying to say, that you will be very careful that this distance, whatever we are saying, is not a Euclidean. It's a d-dimensional distance.
Yes, sir. I meant that only. Sorry. I meant, could we change the definition of that d-dimensional difference to something else? Maybe, um, like make the neighborhood smaller in some sense.
Times, so sometimes a very interesting thing we say, but it is a completely out of context. But one say that sometimes we just one that to beyond a certain amount of universe, we can't ever reach. So in that case, in that sense, there is a concept of multiverse. This is the from us, we cannot even reach. When we are be there in the in this, you can say their boundary, they almost done. So we never reach them. You see that is very interesting. That in an atom, even in an atom, if you see the most of the 90, more than 99%, I think if I'm not very wrong, I have to check. And but 99%, the locality is vacant. You can understand, but can we feel that? We can feel it. So that there's a very complicated structure. So we cannot. So that forget about this. But what if they are here, it is the idea. But some of you has said a very interesting concept that yes, not exactly, your answer is not exactly correct, but it is somewhat correct. Now you see that thing is that now what I'm trying to say, this is not in a your machine learning thing, but just for very interesting. I mean very interesting. That's why I'm just saying. So if this is a very high dimensional space, let's say it's a very high dimensional space. Okay, let's say the 3D is a, let's say for our hypothetically, that 3D is a very high dimensional space. Okay. Now, it is possible that now the problem is that the KNN, if we consider a kind of plane here, so it's a called subspace. Okay. Now this subspace, if we say that all data points are lying within a subspace which is lower dimensional. Let's say it's a two-dimensional in this case. So this space actually, these points are actually in this 3D space. But there is an assumption that even if they are 3D space, they all lies in a plane which is this called subspace, or you can say this is defined with this. So then if it is so, or what you say, that if it is possible that so any other point defined, we can project here somehow, then we can do some KNN over that. Get my point? Now it is actually not subspace. Okay, just a second. It is called. It is actual. The case is bit not exactly this called. It is two-dimensional, but it is called in this case. I don't know if I can write it or not. It's something like this. So it's called submanifold. So actually, this submanifold is not two-dimensional. This may be higher dimensional, but this submanifold is basically the lower dimensional than the actual space, than the dimension of actual space. If this point within this submanifold, okay, then we can do something. Okay, so there is one property of submanifold that is very, very important. Why? Why? Because in submanifold, in a local neighborhood, these distances are in Euclidean. Okay. Can you give a very, very interesting example? So actually, in our art also, when is here and your classroom is there, so this is your, is called flat. So that's why our ancient people thinks that Earth is flat. Earth is flat. So if look, the question is that if I have to write in a different way, that something you can understand. I don't know. I'm not good in the. Actually, its distance is very less, but it is not its actual distance, because its actual distance is basically here. Now you have this. This is a very interesting kind of thing. I think if in a sci-fi, a lot of sci-fi that is used, that is a kind of white hole or something they called it. Some that at least there is one movie I saw that there is a aircraft that is lost in 1940s or something, and it's found to be, I forget exactly the year, and it's now something, it has been discovered in 1974 or something, 20 years later, in some 1975 or something. And that actually, this is the thing that basically this kind of problem is happened. So it has been in not in science but in meta science, or you can say science fiction, that here in some of our art, so maybe you can say Bermuda Triangle or something, there is a this kind of thing is happening. So they actually very short time, they actually go to the future or something. So this is completely scientific, but the actual mathematical orientation of this is this. Okay, this is called submanifold. Okay. And there, if this is the thing, the only thing is that why Knen is basically can be used, because in this submanifold, this local area is basically very kind of Euclidean, not the Euclidean distance. Euclidean distance. Okay. So this is the very interesting kind of thing that we. Okay. So this is the way actual. So here one very interesting And Pekin is one of the Cornell professor. So he's very good demonstration he has shown. What is this? This is the cursor dimensionality problem is demonstrated using. So in this cubic space, what we have just shown actually. Sorry. So this kind of cubic space. Here, the number of points they have used. There's a lot of different points in there. And what he has done, this is the distance between any 2 points in the x-axis. The x-axis, distance between any 2 points. Okay. He calculate that there is this is uniformly random distributed. Okay. So then it's uniformly random distributed, so that any 2 distance between points they measure and take a histogram out of this. So this is 0, 0. This means the 0 distance between 2 points. How many such 2 points? The in between the distance is 0. Then the distance is 1. Distance is 0 0.1, 0 0.2, 0 0.3, so 0 0.5, and so on. In this histogram, they are just plot it. And here the frequency. Frequency means how many such pair of points. And this is the 2-dimension. Now, if 2-dimension, you see the most of the point in this cube or this 2-dimensional, this is not cube, this is basically 2-dimensional, it's a square. It is 0.5. And it is actually root 2, 0 to root 2, in between these two. Okay. So it's a cubic. So it is in between this. Now, very interesting thing happening. If we increase the dimension, so if we increase the dimension, you see the number of points. This is tail part is increasing, so it's become 1.5. And now the thing is that this curve is basically shrinking. And now it is the most of the point is greater than 0.5, 0.75 or 0.7, something like that. Now you can see more interesting when it's a 10-dimensional. Now with that, it's the average point, or the most of the point is 1.5. So what is the average number of distance between 2 points? Any 2 points are increasing with increase of dimensionality. Now you see here, it is at 100 dimension. So it increased, it become 4. And you see that there is no such point in 0.5 at all. Here also, there is no such point in 0.5. Here there is a less than, so it's a 2 now. So it's greater than 2 or 3. Getting the point. If it's 1,000 dimension, it's basically narrowed down. Histogram plots so that the distribution of arrow is distance between randomly distributed point with a d-dimensional unit square. As the number of dimension grows, all the distance is concentrated with a very small range. So not exactly what we have said. So that in a very high dimensional space, any 2 points are very highly separated. That is very much understandable from this. But now I have one question. So most of you know this kind of face recognition problem. This is high dimensional. Okay, but we easily use this recognition. The Canaan kind of algorithm to somewhat it works. Can you? Any answer?
Excuse me, sir, am I audible?
Yes, yes.
Sir, can we perhaps boil the like structure of a face down? Like suppose rather than considering everything that in terms of data, can we consider some things that only those things that matter? Suppose the distance between the eyes, the distance between nose and eyes, and all those things. Basically, get into smaller dimensions. That is
No,
what I.
you are not properly audible. Please repeat your answer.
I am saying that the major problem with this is we have very high number of dimensions, right? And we just studied the curse of dimensionality. So we can try to reduce the dimensions by considering only the things that would matter while determining. So maybe I can consider one of the dimensions as the distance between the eyes. Then I can consider one of the parameter as the length of the face and all those things. Like I can boil down the number of dimensions.
Yeah, kind of answer okay, but not exactly. So first of all, if any other answer, other than then I say. Now, first of all, the image, this or kind of handwritten image, is not uniformly randomly distributed. Actual problem of this, whatever, so this assumption, if it is uniformly randomly distributed, in our practical world, very less things are uniformly randomly distributed. But if it is uniformly randomly kind of distributed, then it's a kind of white noise and it is no use. So that is one thing. Okay. And your whatever you have tried it bit true also. Because if you see in a very practical cases, now sometime in the police station, if some crime happens, there is some sort of sketcher, or there is a very who is artist kind of thing. They are being hired to sketch the culprit or this who is basically suspicion. Somebody said something, maximum 30, 20 to 30 points about kind of people of kind of suspicions or what we basically considering that who did the crime. And he write, he draw this thing. So it essentially means that even when it is we were doing is a very high dimensional face recognition algorithm, that will take in very high dimensional, maybe kind of 100 dimensional, 200 dimensional. It's not that much important, that dimensionality. If you say that you have some of your friends picture you just show to your another friend or your parents. That look, this is a new friend of mine. Now you never said that top left corner or top bottom corner pixels is this. You never going to say in this way. But the thing is that so when it is a, but don't this with the human perception or human cognition, this is a much more you can say intelligence is there, but still it is the case that the it is so that most of the feature, important feature, is not that much high. So you can you can if you somebody know the PCA or a singular value decomposition, the same thing. Actually, what we're basically saying, that what do you mean by PCA? PCA is I'll come to the PCA in this course. So actually, it's a coordinate transform. So coordinate transform means what? We a particular data clouds or data a point clouds define a very high dimensional space. Now, what we are saying, if we can to find a particular coordinate system, definitely much lower dimensional than that of the actual dimension thing, that most of the energy of, or we can say energy because this is a technical term, that is being represented in space or that particular time. So that is your principal. So if you have a particular principal component axis, so in this axis, the most of the point is oriented. Okay. So data points means data points are oriented. So that actually we try to find out. A similar thing. So this is the actual reasoning, and it is one of the important concept of machine learning. That in a particular dimension or the actual data point, the points of concerns are lying. If it is not, it is when it is not lying, when it is uniformly randomly distributed. But most of our practical problems, which follows a particular distribution, but unknown distribution, we don't know the image distribution, we don't know the face distribution, we don't know the hand digit distribution is not required to know. But it somewhat follows a particular distribution, then it is possible to represent that data points in a some submanifold or kind of subspace with a lower dimension. And if you find this dimension, you are done. You can very easily analyze this. This is one of the very important concept of machine learning that you have to take. So it will come in SVM when it is with the kernel trick. It will so different ways it come in the singular value decomposition when in the PCA. All this the same that we have to take care. Okay. So any
Can
questions?
you repeat this point again? This last point which you said about what you can observe in a particular dimension.
What? Please repeat your question again.
Just the last point you mentioned, sir, that in a particular dimension, if it's not uniformly randomly distributed, what will happen?
Yes. That the thing is that if it is uniformly randomly distributed, it is very tough to find out a particular subspace, okay, where all these points are there. Because actual what happened, every point has this kind of tendency to be clustered in a particular dimension. And that this inclination is basically driven by its distribution. But if it is a uniformly distributed and uniformly randomly, it is a completely haphazard. Tough. They trying to find out that particular submanifold or kind of subspace where most of the points are lying. It's the same thing of your principal component. linear hyperplane that separate out your classes, linear hyperplane. So it's a linearly separate. So in a particular subspace, these data points are linearly. And we transform this to another dimension. Where this is another way to solve the problem. Okay, that is I'm trying to say. And this is all. Okay. This is taken some very good this thing. They use basically I think you see that Euclid this basically the distance, different distance they have used. They use some left the first, this particular is the Euclidean distance. This first row actually, the first column, it is Euclidean distance. This is city block. This is maximum difference. So these are the distance, different distance they have seen. And this how this KNN classifier works. Okay. So now this is first of all where now it is, and not only that, it is k is equal to 1. This picture. This for this particular is k is equal to 1. We can say this k is equal to 1. Now it is k is equal to 3. Okay, is equal to 5. So it is basically number of points within you. K is equal to 7. So here you can see that how actually this boundary is being defined. So city block distance, sometimes there is some problem happen. So here also it's good. And now it is basically that Euclidean distance k is equal to 9, k is equal to 9, this is it is city block, the maximum difference. Again, k is equal to 11, 13, 15, and so on. You see, if so, definitely k value is also a very important aspect. Here, actually, so that what about the optimal k value? So it is not that always if you take a very high. So actually, so if you just try to understand what I'm trying to say here, that k means what? The number of neighbors. So actually, if you say that in this way, so if this is the data point, you see the number of, this is the k. So it is a k is equal to 3. Now, if we say the k is equal to 5, then it is this, or k is equal to 5. Now, if it is a k is equal to 7, it will definitely take this. So it is the k is equal to 7. So, but you see the k is equal to 7, this clustering is not that much good because it will take in that 12. If k is equal to 9, it will take, and k is equal to more than 9, it will take the whole space. So there is no kind of, so this k value is very much data dependent. Now for the particular data set, this k values varies. So if it's a very high dimensional, so densely distributed data, then k, maybe higher k is bit better. But if it's sparsely distributed data, then k of some low value. So we can summarize this KNN in this way. This KNN is a very simple and effective classifier if distance reliably reflects a semantically meaningful notion of dissimilarity becomes truly competitive through the metric method. If n greater than n is basically infinity, kn becomes probably very accurate. N is total number of data, but very slow. Okay, so definitely, if it's a very high number of data points, then k means will work. But the dimension is high. Point drawn from the probability distribution stop being similar to each other, and kn assumption breaks down. That is the disadvantage. Okay. So this is the basic understanding. The kn is a very simple classifier. We saw another very simple but a very fundamental classifier, that is and we'll show that how this basically evolved or basically generated from a very naive statistical make a very fundamental. And if you have any question, you please ask and take it. Please don't. Yeah, I'll take this here.